All right, everyone. We have our last talk of the day. It's Tikhon Jelvis with some information, thoughts about the Z3 SMT solver. All right. Thank you, Tikhon.
Right. Okay, so as a few people have noticed, there's something of a SMT solver sub-theme at the conference this year. And in some sense, my talk is maybe one of the more introductory ones to how you could use an SMT solver. And while I have some code in Haskell, and it uses Z3, none of the ideas are specific to either, and you could use them in any language with any SMT solver. But first, let's again review what an SMT solver is. So it all starts with the Boolean satisfiability problem, which is a classic NP-complete problem, which in practice we can solve surprisingly fast for real-world instances. So there are two things that make it interesting. One of which being that we have fast SAT solvers, and the other one is that it's actually relatively easy to encode problems in terms of SAT as opposed to other NP-complete problems. And the way SAT is formulated is you have some number of Boolean variables which are ANDed, ORed, and could be negated. And the solver tells you whether there's any assignment of true and false for each variable so that the whole thing holds true. So it either gives you the correct assignment or it tells you that it's unsatisfiable or unsat. What an SMT solver does is it extends this idea with other kinds of variables. So we're no longer limited to Booleans, but instead we could have constraints over numbers, arrays, and, well, other things. And the advantage here is that it's even easier to encode interesting things in terms of SMT than it is in terms of SAT. In some sense, you could think of SAT as being a lower level version of this, where you have to do everything literally bit by bit, where SMT lets you do things at a higher level. And also the solvers have more domain-specific insight in the kinds of variables they provide, letting them solve certain problems faster. So the different theories correspond roughly to the different kinds of variables and the different sorts of constraints that you can express. And there's a bunch. I mean, I listed the ones that seemed the most easy to understand, but Z3 has, 30, maybe more. There's a lot of capabilities. And one that's worth seeing in particular are the fixed-sized words, so like machine words. Basically, it's just a sequence of bits where Z3 also knows how to do the common bitwise operations, including treating them as numbers, so addition, multiplication, division, for both signed and unsigned, and the normal bitwise operations you see in languages. And one thing that's a pretty recent advancement is that sort of built on top of bit vectors, solvers now support theories of floating point numbers. So you can actually represent a floating point number as the actual set of bits that it is, as opposed to trying to approximate floating numbers with real numbers. Now, that might sound kind of weird, because normally what we do is we approximate real numbers with floating point numbers. But as soon as we start caring about the correctness of programs, it's often actually easier to go in the opposite direction. But with these with the new theory of floating point, we can actually model programs with floating point numbers completely correctly. And I mean, I won't come back to floating point numbers in this example, but it should be clear that if we just replace every time I use integer with floating point, and we use the theory of floating point numbers, we could analyze programs depending on floats the same way we do the ones that depending on fixed size integers. Okay, so Z3 is the specific SMT solver I'm talking about, and it tends to be the default SMT solver everybody goes to first. Usually, unless they have a good reason, they're probably going to depend on Z3 because it has a sort of sterling reputation and a lot of different theories. For a long time, it was sort of relegated to academic research because Microsoft released it under a very restrictive license. But I think it was this year or last year, they released the entire solver under an MIT license, which means you're free to use it for whatever you like, including commercial applications. And it has API bindings that are useful to, I imagine, everybody in the room. Like I'll be using a package in Haskell, but it also has an OCaml API, as well as one in C#, which presumably you could just reach out to in F# as well. Okay, so Haskell has, well, it has multiple packages for working with SMT solvers, but the two that I'm familiar with are SBV, which is a sort of high-level DSL which supports multiple solvers, and then the Haskell Z3 bindings, which are Z3 specific and expose certain capabilities that SBV doesn't. So if you just want to experiment with SMT, SBV is a great place to look. But I think if you're building a tool or you need to integrate closely with Z3, the Z3 bindings are more interesting. So the example code I'll have later, and the example code I have on GitHub for this talk, uses the Z3 bindings and is specific to Z3. Okay, so the main thing I'm going to talk about is how we can take a program and compile it to an SMT formula. Then once we've got the program as an SMT formula, we could use the solver to answer all sorts of questions about it. So the first thing to ask in a formula is, what do the variables represent? And the main encoding separates these into essentially three groups. We have one set of variables for the inputs to the program. We have a set of variables for the outputs, like what the result is, and also a set of variables for every single intermediate state that the program goes through. So in a sense, the formula represents a sort of symbolic computation trace through the entire program. So a good way of thinking about it is that by solving this formula, we can make statements about all possible computation traces that your code can take. And you can see why this would be very powerful. Unfortunately, the downside is that actual programs can take a lot of different traces, and sometimes they can loop forever. So we can't actually handle things like loops directly, which means that we have to find some way of encoding a loop in a way that that is that an SMT solver can handle. And the specific technique I'm going to describe is bounded. So we basically say loops are difficult, so we're just going to arbitrarily bound loops at, say, 1,000 iterations or 10,000 iterations, and then just unroll them. So in essence, we just completely skip the question of loops altogether. Of course, if you're interested in doing something else, you could mix this approach with, say, some preset loop invariants and have a different way of analyzing loops. But as soon as you get to allowing programs that have arbitrary looping, you hit the limits of sort of Turing completeness and Rice's theorem, where there are all these questions which you just fundamentally can't answer. And bounded verification lets you trade off the fact that you have this arbitrary limit for the fact that you can sort of treat any sort of program without worrying about these things. Okay, and so we have this formula, and we have our variables that are inputs, intermediate states, and outputs. And the easiest thing we could do is we could fix the outputs, and then we could solve for the inputs and the intermediate traces. Other way around. We can fix the inputs and solve for the outputs, which just gives us a normal interpreter. But since this is just a normal logic formula, there's no directionality inherent to it, and we can solve for any set of variables we care about. So if we fix the outputs and solve for the inputs, we get a reverse interpreter. And by its nature, the reverse interpreter has to be non-deterministic. Like there's multiple possible input states that give a given output. And the SMT solver can handle this, and you can just get either all the possible solutions or the solutions one at a time. And then we could also actually look at the intermediate states of the program. If we have some invariant that we want to hold, we just add an extra constraint, an extra assertion to every single state that the program can assume, which then lets us solve for whether the invariant is always true or in which cases it breaks down. And we can actually use this approach for bounded verification, where we have some specification, like, say, another program that we know or believe to be correct, and we can ensure that it always gives the same output for the same input as another program. And this is another way of thinking about this in particular is it's sort of like a symbolic quick check, where with quick check we have our little specification and we just randomly generate tests and hope to hit one that fails if there is a failure. Here we have the same idea of having a specification as a program, but we actually use the solver to symbolically test every single possible input and every single possible output. Okay, so I'll go through a sort of slightly detailed explanation of how you would convert a program to a formula. And the first question is, what language are you using? And obviously, the bigger the language, the more difficult it will be to write a formula compiler. So I chose the smallest language I knew of, which is imp. And if anyone's taken a sort of programming language theory course, this is the language that's classically used to teach about operational semantics, because its operational semantics are as simple as possible. Another way to put it is that this is an imperative language for which it's as easy to write an interpreter as possible while still being at least somewhat interesting. And this makes it a good choice for writing a formula compiler, because in a sense, the formula compiler compiles the operational semantics of a language into a sort of logic that's understood by the logic solver. So the simpler we can make it, the simpler the formula compiler, and the easier our job will be. Okay, and so the language itself has sort of two pieces. It has expressions, which can be numbers or can be booleans, and the expressions can't have any side effects. All they do is evaluate to a value. And the variables, for simplicity, are always ints. And in my case, they're always 32-bit wide integers. And then we have commands which have side effects but don't evaluate to a value. So all they ever do is change the state. And here we have assignment, we have while loops, if statements, and ways to sequence commands together. So normally, imp is presented defined as a sort of abstract grammar. So here we have the arithmetic expressions, and we have variables, we have literal numbers, and we have all the usual arithmetic operators that you're used to. But the really nice thing with using a language like Haskell or OCaml or F# is that it is really, really straightforward to translate these abstract grammars into types. In fact, it's so straightforward, it's almost pointless to show the two, except to show that they're kind of exactly the same. If you were sort of, back in the day when people only used ASCII and you had to write out this grammar, it would look almost exactly like this. The one weird thing for non-Haskellers is that the last four constructors, the plus, the minus, and so on, are all infix. So just like you can define custom infix operators by using special symbols for your function names, you can define infix constructors. So the arithmetic expressions look like this. The Boolean expressions, you could figure out what they are, but they're really not very important here. And then finally, we get the commands. Now, the grammar for commands is still pretty straightforward. It still has the four constructs I mentioned, as well as skip, which we use to have empty blocks, so empty if statement branches, for example. And the main reason it's useful to look at the type is because all the code from here on out is going to sort of follow the type, the shape of the type here. So all the code is going to pattern match and do different things depending on which construct it is. And the way I like to visualize this is that the type is a sort of skeleton, and the code is a sort of layer of skin which we lay on top of the skeleton, and it naturally assumes the shape that the types provide. And this means that our problem is immediately broken up into a whole bunch of small pieces. So instead of trying to compile the whole language, we now have the problem of compiling skip, and the problem of compiling set, and the problem of compiling seek, and so on, all separately. And this naturally makes the entire effort a lot more tractable. Okay, and so to convert to a formula, there are basically three steps. The first one is inlining all our functions. Now, I didn't talk about functions here, And the main reason is because after we inlined them, we can just pretend we didn't have any. Then we unroll all our loops, and we transform it into SSA, which is single static assignment style. And I'll go into what that means in the next slides. But so inlining, again, if we had functions, basically all we do is we create fresh names and then paste the function body into where it was called. So this is sort of how the C preprocessor works, except I think it doesn't even create fresh names. So as you can imagine, but the biggest advantage of inlining, of course, is that our formula doesn't have to know anything about functions. We can forget about function names, and it's just as if it was all straight line code. And obviously, you could run into the problem of recursion. But just like we're going to have an arbitrary bound on the length of our loops, we would just have an arbitrary bound on like how far we're willing to recurse. Okay. Yeah.
So you literally unroll?
Yes. So sorry. Yeah. So the second step is unrolling loops, where basically we take a loop in the form of while x something, and we just turn it into a whole bunch of nested if statements. And realistically, each loop is going to be unrolled to maybe 100, maybe 1,000 steps, depending on your application. So if you actually took the program and you printed it out, it would suddenly become very long. But luckily, the SMT solvers are fast enough to handle surprisingly large formulas. Although I should make a side note about performance, is that I've worked with SMT solvers for a little while, and I've worked with people who've spent a lot of time, years and years, using them, and performance is still a bit of a black box, I think, pretty much for anybody who isn't actively implementing an SMT solver, and maybe even for them. So it's a bit hard to predict ahead of time how long a formula will take. As a rough heuristic, the larger your formula, the longer, but that doesn't actually hold if your formulas are too different. So it's really hard to figure out what will run quickly and what won't. Okay, and so single static assignment, this is the part where we really take the sort of directionality inherent in executing code and transform it, translate it to the logic layer, which has no inherent directionality. So from the SMT solver's perspective, the logic formula does not happen in any particular order. So we need some way to structure the formula to maintain the order of the program. And the way we do it is by turning every single variable at each time step into a new name. So if we take x and then we set x to something new, in the formula we would have x0, and then we would have x1, and we have a constraint that says, oh, x1 is equal to like x0 plus a0. If anybody here has taken a compilers class, you've probably seen SSA before, because this is an intermediate form used by a lot of imperative style compilers. And it happens to be a really good fit for expressing as a formula. The one tricky part with single static assignment is how to handle if statements. Because here, all of a sudden, we're in a position where, depending on which branch we take, x will have a different value. And there's no way to tell statically which one it will be. And so, at first, the solution in real actual SSA feels like a bit of a hack. But again, it happens to work well for SMT solving. But essentially, what we do is after we're finished with the if statement, we create a new variable, x3, that basically has a magical oracle function that says, oh, if we took the first branch, x3 is equal to x1, and if we took the second branch, x3 is equal to x2. And these are traditionally called phi functions, and basically let us extract the conditional decision part of the if statement into our SSA form. Okay, so the next question is how do we actually compile these things? And I think especially the part with the phi functions will make more sense once we see how they're turned into a logic formula for the SMT solver. But one thing that kind of struck me was that the formula compiler looks a lot like the interpreter. And for most of the implementations, if you squint, it's kind of like we're interpreting the code in some weird sort of way. So for comparison, I'll just in parallel give you parts of the interpreter for imp and parts of the formula compiler that produces the Z3 AST and the set of Z3 assertions. And in both cases, just like we had three separate types, we had arithmetic expressions, Boolean expressions, and commands, we have three functions. And in both cases, we're going to keep track of all of our variables in some sort of map, a scope. And so, similarly, in the interpreter, the arithmetic expressions and the Boolean expressions can read variables, but they can't edit them. So all they produce is their result, which is either an int or a bool as appropriate. And in the case of the SMT compiler, they actually produce fragments of a formula that aren't ready to be sent to the solver yet. They're just sort of like parts of a formula which don't necessarily evaluate to a full constraint. So we'll be using these ASTs to build up a whole constraint, which ultimately can be solved and evaluates to either true or false, sat, unsat. And then finally, commands. In the interpreter case, all the commands can do is they can edit the scope, they can change variables. So we just return the new scope. Again, if this was a more complicated language where, for example, commands could have values, we'd need a lot more plumbing. But here, for the sake of simplicity, we just always return the new scope. And similarly, for the sake of simplicity, I'm assuming that the programmer is perfect. I am, so it's fine. And that nobody ever makes any scope errors. So the variable is always going to be in scope. And so finally, in the case of Z3, once we actually run a command, we can just bundle it as its own assertion and give it to the solver. So instead of returning an AST that needs to be combined with other pieces, we just assert directly, which is why the type of the command compiler is just a Z3 of unit. Okay, so the first thing is arithmetic expressions. So what we want to do is we want to compile something like the expression 5 plus x into an expression which says, add two bit vectors, one of which is a bit vector literal 5 that's 32 bits wide, and one which is the variable x0, 32 bits wide. And this is just one note, is that sort of, if you actually looked at the SMT formula, it is kind of painfully explicit, both about what sort of operations you're using. I mean, in this case, addition is easy, but in other cases, you have to tell it whether it's signed or unsigned. And you also constantly have to tell it how wide literals and variables are. And so pretend that each of these little extracts is part of a large pattern matching case statement that matches on the structure of an arithmetic expression. So in the case of an interpreter, if we see a literal, we just return that number. In the case of the Z3 formula compiler, if we see a literal, we just make a 32-bit vector with that size. So we just produce a literal formula. Similarly, in the case of the scope, it's actually exactly the same, because we're keeping track of the variables in both cases. It's just that in the original case, the scope has ints, so we just give it the final value. In the case of Z3, the scope has sort of symbolic variable names that the solver knows about, and we just tell it, use this symbolic variable. And then finally, to do something like plus, in the interpreter case, we just recurse directly. And in the Z3 case, it's a little bit more difficult, because everything is being managed by the Z3 type, which happens to be a monad. So we have to sort of explicitly extract the results of the two recursive calls, and then make an addition node in our formula. So also, just for a note, these little Unicode subscripts are totally valid Haskell. So you could actually use names like this in your code. And you can configure Emacs to make it easy to type. And then all non-Emacs users will hate you. But they had it coming. OK. So, I should add that the rest of the expressions, both arithmetic and Booleans, are basically the same thing, except instead of making an addition node, you might make a subtraction node. Or, instead of making a literal number, you make a literal Boolean. But the shape and the structure of the code is exactly the same. OK, so the sort of commands are a bit more interesting, because they're the ones that actually change the state. And the way we do this is by extracting each command into its own assertion. And at the end, Z3 gathers up all the assertions and makes one big formula. So conceptually, this is the same as making a big formula full of ands, but we just let Z3 simplify the process a little bit and give it the assertions piece by piece. This is also nice because of a feature somebody mentioned in the previous talk called incremental solving, where once we've solved the problem with some number of constraints, we can actually add new constraints, and the solver can resolve it, still taking advantage of all of its previous internal state. And this lets us sort of refine our formulas without a big performance penalty. We can take a formula and add constraints without having to redo it every single time. And so in the case of the imperative assignment statement, or set in my type, we just create a new variable x1 and assert that it's equal to the right-hand side. And the right-hand side, of course, is compiled exactly the same way it was in this previous example. Okay, and so in the interpreter, all we do is we update the scope. In the formula compiler, it's a little bit more complicated because we're only really maintaining the scope for our own use. So we also have to, create a new variable in Z3 and add the new assertion. So there are actually three sort of Z3 operations that we do. We create a new variable, and this is a really convenient feature where we just give it a name and tell it to make a fresh variable, which is kind of like a new variable with the same name that's distinct from all the other ones. So this keeps us from having to manually keep on updating a counter and calling things x1, x2, etc. And then again, for the actual equality assertion, so here the equal sign, we have to explicitly make the equality node in the AST. And finally, we just use Z3.assert to sort of feed it to the solver and add it to the set of assertions that we're solving. And then finally, we update the name in our scope. So the reason we're keeping an explicit map as part of our formula compiler is so that all these fresh variables are mapped back to our own name. So by doing this, we just let Z3 take care of the making variables fresh. Okay, and then if statements. So these are the tricky ones. And basically, the reason the phi functions made sense in SSA is that Z3 actually has something akin to a phi function where you give it a condition. So whatever condition was in the if statement goes into the expression, and then it just solves for the condition and chooses the appropriate one. So in a sense, this is like a symbolic way to do an if statement. And in the sort of so this slide's a bit different because if statements look completely different than the interpreter case. In the interpreter case, we just branch and do the right thing. Whereas in the Z3 case, we always compile both branches because all the branching happens symbolically. And so the way we do it is just, we recursively compile both branches. And then after that, we add a sort of a phi function for every single variable that got changed. And as it happens, these functions in Z3 are called ITEs, which stands for if then else. So really, all this expression is saying is that if the condition is true, we took branch A. If the condition is false, we took branch B. And then the solver handles, all the difficult lifting symbolically. Okay, so you'll notice I skipped loops. And that's because after unrolling, we don't have any loops. So we've actually made the language significantly simpler and went down to 3 constructs. So that really was more or less the whole compiler. I skipped some of the parts for expressions, but the commands are all there. And now that we have a formula for our program, the question is, what can we do with it? And as I mentioned earlier, we could use it as an interpreter, which is kind of pointless because it would just be slower. But it's nice to be able to test that our formula actually makes sense. We can use it as a reverse interpreter, which is something of a parlor trick more than being useful. But we could also start checking invariants. And this is a technique called bounded model checking. Where basically we just specify an invariant in temporal logic. So temporal logic lets us take some property of a program, say, or a program state, and quantify it over time. So we can say that, oh, we have this property here, and it's always true. Or we have this other property, and it has to eventually be true. And, I mean, depending on the logic you use, there are other operations. And among other things, this is a very natural way to encode safety and liveness properties for concurrent programs, which I won't get into. And so the main part with temporal logic is that the logic itself is implicitly quantified over time. And usually when it's formalized, time is like a set of natural numbers. So in our case, all that time is the different sort of slices of like x1, x2, x3, x4. So whenever we say that something is always true, it just means that we run the predicate through and we just have a big AND statement which says, oh, this is true for x1, and this is true for x2, and this is true for x3, and so on. I mean, there's a bit of bookkeeping to deal with conditions again, but that's the core idea. And then, of course, the eventually true, it's often is like, just turns it into or. So like, it was true at some point. So it's also nice to note how these two operators are duals, and then when we encode them, they naturally encode as and which are also sort of dual in nature.
So like with loops, you unroll the quantifier.
Yeah, right. But because essentially the quantifier, like, if we say that x is always true, we're saying it's true for every iteration of the loop. And now that we've unrolled the loop, we just attach the quantifier to every single step. Okay, so the next part is that we can actually verify programs against each other. And basically, we take the outputs, and we assert that the outputs are not equal. And then we solve it. And if we've solved it, that means that the programs are different, something is wrong, and we get the input that caused the mistake. So we get a sort of counterexample. And if we can't solve it, that means the program was correct. Honestly, this is a bit confusing at first, because normally you're used to the fact that something is satisfied means the result was true. But here it's exactly the opposite. Okay, so once we have verification, another thing we can do, and sort of the first place that I ended up using an SMT solver was to actually synthesize programs. So with a bit more clever encoding, we can actually create variables that represent sort of parts of the program. So like expressions or instructions or what have you. And by fixing the inputs and the outputs, we can have the SMT solver find a program that actually satisfies the input-output pair. And the way we take this from just solving for a single pair or multiple pairs to solving for a general program is by verifying it against some specification. And the way this works is we take one input-output pair. We solve it. We get a program. Now, since we only gave it one pair, the program is probably wrong. So we run it to the verifier. The verifier tells us, well, this is wrong. Here's a counterexample. So we take the counterexample, and we put it back in the synthesizer. Now we have 2 points. So we synthesize that. We find the program that works for both of those points, and then we go back to the verifier. Now, at first, it seems like this might take a long time. And okay, it does take a long time. But the important part is that it takes far fewer steps through the verifier than you would think. Because conceptually, each time we find a counterexample, we found a new edge case in the algorithm. And so it turns out that we can quickly prune the search space in only a few input-output pairs for most programs. Okay, and so one way to use this is to just optimize code. So in some sense, this is like the most direct way to optimize something, because we say, well, here's a program, find a faster one. And then the solver finds one. And so this is great. As I mentioned, it's slow. So realistically, you won't be optimizing large programs. But you could, for example, optimize programs with a little sliding window. So vaguely similar to peephole optimizations. And it turns out that it's actually easier to write an optimizer this way than it is to write a classic optimizing compiler like GCC, because it requires a lot less domain expertise. And I mean, I can actually sort of say this confidently, because I worked on a compiler that used this to optimize, and there's no way I could have written all the rules by hand. And in fact, like, I understood the architecture we were compiling to well enough to like simulate it, but not well enough to write real programs by hand. But that was, that was totally fine, because all we need is a formula compiler.
Stop these human beings.
Yes, exactly.
important advantage.
But of course, optimization isn't the only thing we could use synthesis for. Another way to handle the fact that we can't deal with large programs is this approach called sketching, where essentially the idea is that a programmer often knows most of what they want. They know the shape of the code. They know that they'll need a loop here, a condition here, these variables here, but they don't know all the details. And, well, we can actually write tools which let you write a program, leave a bunch of holes, and have, add some assertions, and have the synthesizer just fill the rest of the program in for you in a way that satisfies those assertions. And so there's an existing compiler from Berkeley that does it for a Java-like language, but that's not all that exciting. But I recently stumbled across a project called Synquid, which uses refinement types. So like Liquid Haskell, but in a language that's not quite Haskell, and then lets you synthesize the implementation of functions just based on their refinement type. So, and like you can actually go and play around with it online. So that's, I'll have a, well, I don't have a link on my slides, but it's worth just checking it out. And at some point, you might expect to see this for Haskell, say. And then there's all sorts of other things that you could do with this sort of technology. One that I think is particularly interesting is creating interactive tools that can help a programmer as they're programming. So one idea is to use this to model concurrency perhaps, or actually like give you execution traces, even potentially of a program that you're sort of in the process of writing, which is the idea behind this technique called angelic programming. And in general, you could use SMT solvers as debugging aids. You can use them to generate test cases. And that particular one is a good approach because you don't care how long it takes you to generate test cases because you do that once. And then you can run the actual test cases as many times as you like. So even if it takes you a few hours or days to generate, your test suite, all that really matters is how fast the test suite runs, each time you make a change to the code. And then I imagine there's a lot of interesting stuff with synthesis-powered code completion. So you can actually like infer what the programmer wants to do and give hints. And I think one of the most important insights, though, is that pretty much everything I listed for a full-blown language would be a research project and likely multiple research papers. And in fact, some of these tools exist for languages, but the problem is real languages are big, they're kind of messy, and they're annoying to work with. But if you have some sort of domain-specific language, you're in a much better position to build tools on top of an SMT solver because domain-specific languages tend to be much smaller, and they're also often bounded by their very nature. A lot of domains don't need unbounded looping. They don't need Turing completeness. So you might actually have domain-specific languages where something like bounded verification is as good as you would want it. And of course, presumably you as a programmer understand a domain-specific language that you designed way more than you understand whatever general-purpose language you're using. Just because, again, general-purpose languages are really, really complicated. Anyway, I picked up all of this stuff at first by taking a program synthesis class at Berkeley. And while I doubt it'll be offered any longer because the professor moved to a different university, all the resources are still available online. And you can see the slides and a lot more details on different techniques for program synthesis specifically. And then also I have links to my slides and a whole bunch of papers on my website at jelv.is talks composed 2016, which, if you really want to dive into it, will give you a good starting point to see different ways people use SMT solvers, use synthesis, do bounded verification, and so on. And finally, I think I'll be at the Unconference this weekend. So if anyone's interested in playing with SMT solvers, I'd be happy to help or to guide you in the right direction. Okay. Yeah. Okay.
I was just wondering, when you showed that, that iterative procedure used to generate a program, start it, find a case where it wouldn't work, and did several, what were some of the problems you gave it or specifications?
So, like, the one project where I used this approach was a compiler for a weird architecture, and the specifications were programs in this sort of low-level forth, and like we used it to optimize them. So normally when you think specification, you think some sort of high-level logic, but here we just literally took fragments that we naively compiled to forth, or this really weird dialect of forth, and used them as a specification to find faster ones. Okay, somebody else? Or
Hey, awesome talk, by the way. So when you were talking about reverse interpreters not being as useful, an example popped into my head for like, I work in security, so actually it would be really awesome if I could take like a string manipulation language and then look, I know what my exploit should look like, but what should it look at like at the input? Like that would be really cool.
Yeah, so I mean, perhaps they are useful, but this is also one of the places where the sort of unpredictable performance comes to bite you. Because obviously running a program backwards is fundamentally way harder than running the program forwards. But one of the interesting things it turns out is that usually what happens is if there is some input that gives you an output, it's really fast. But if you wanted to fully prove that there's no possible input, it becomes kind of dicey and depends on like how far you unroll your program, how complicated it is, and so on. But if you don't care about having like 100% verification, you could just say, well, I'm going to run it for 10 minutes. And if it gives me a counterexample, it's good. And if it doesn't, well, it's probably fine. And yeah. Okay? Sure.
Just a few comments. First place, thank you. And thank goodness this is coming down the pike right now, because there's a huge movement in this country to force children to learn how to program in C. and I think this will deal the death blow. Oh, one more comment. Okay, so suppose there are no ifs in your thing. It's got plus and times. Then, of course, we have algebraic geometry, and we have the general problem of interpolation by a polynomial, or maybe if it's got division, a rational function. So I'm sure it's well known in the field. Yep. As soon as you add an if, you then get the cylindrical decompositions for the reals and stuff like that. But thank you.
Yeah, and I mean also like everything I did just used bit vectors, which means that they're just 32 bits, and the solvers do support unbounded integers. But like the decision procedure for that, like the way they solve equations using integers is different and has completely different performance guarantees. And also like with this approach, you can often guarantee that the formula will finish in a finite amount of time. But with something like integers, you get into undecidability pretty quickly. But obviously, since we're willing to do bounded verification, where we just arbitrarily say, we're just going to stop after X iterations, we're not giving you 100% promises pretty much no matter what. Okay.
All right, well, thank you very much, Tikhon.